As this is the last lecture of our semester, I wanted to start with a really open-ended question. Have we learned anything this semester? I hope the answer is yes. I hope you can answer yes right now. However, if you can't answer yes right now, hopefully in the next 30 minutes that we go over pieces of the semester all the way from the beginning all the way to the end and try to integrate them all into the topic of medical technology, you'll be able to say that, yes, I have learned a little bit of something, and hopefully see how it can go forward and be useful in your medical career. I know sometimes it didn't always seem like the most specifically pertinent to medicine, but hopefully this helps tie everything together. So again, this week we're talking about medical technology. And in order to talk about medical technology, we first need to define what do we mean by medical technology. And I think everyone probably has an idea of what this means, but to break it down a little bit, technology is the application of scientific knowledge for practical purposes. So this is really broad. We think of early technological advances like the wheel and fire, which are obviously nothing near computers or MRIs or something that we would use today, but they're still a form of technology. So when we're talking about technology, we're going to think about it really broadly, and that medical technology is any application of scientific knowledge for practical purposes in medicine. So this could occur at any point within the disease process. So it can happen before disease occurs, and this is called prevention. So on the top, you might recognize this. This is a malaria net. And a malaria net is used in places where malaria is endemic, like much of Central Africa. And this prevents mosquitoes from biting people. And since mosquitoes carry malaria, since it's a vector disease, and mosquitoes are that vector, by keeping mosquitoes from biting people while they sleep, we are preventing malaria. And so this is obviously a really low cost intervention. It's a very low cost and simple medical technology, but it saves as many lives as MRIs or ultrasounds, which are much more high tech. On the bottom, we have something we've also talked about a fair bit in this class, which is vaccines. And so, for instance, if you are given a hepatitis B vaccine, then we are going to prevent you from getting hepatitis. And so, again, this isn't technology in the traditional sense that we might think about it, like phones or laptops. But it's still technology because it's the application of this scientific knowledge for a practical purpose. And the practical purpose in both the case of mosquito nets and in the case of vaccines is prevention, preventing disease from ever occurring. So if we had perfect use of both mosquito nets and vaccines, then we would have much lower rates of disease in the population. The next step is diagnosis. So on the top, this is a CT scanner, which we're going to be talking about a little bit more in a bit. And on the bottom, we have the very first X-rays. And so in both of these instances, we are looking at the body and in most cases taking some kind, in the cases that we're talking about, some kind of picture of the inside of the body in order to determine what's wrong. So somebody shows up with symptoms. In this case, we have not prevented disease or injury, and we need to know what's wrong. And so diagnosis is this process of figuring out what's wrong, and we can use medical technology in these steps. And I think this is probably, when we think about medical technology, the step that we most often think about. So you go to a hospital or a clinic and you get into some kind of machine, and then the machine tells you what's wrong through interpretation by your doctors. Finally, after you have disease and after it's been diagnosed, you know what's wrong, treatment is also a part of this process, and is also a place that medical technology can come in handy. So on the bottom, we have antibiotics. And so again, we might not think about these as technology, but they really are. It's an application of the knowledge that we have about the bacteria that is infecting you, and trying to fight off that bacteria. On the top, we have something that we're going to talk about quite a bit, which is a type of insulin pump. And so this is more visible to us as a type of technology, right? It has a screen, you input information into it. But this type of technology, much like the antibiotics, is a way to treat a disease. And so in this case, we're treating diabetes, but it can also be used to treat things like thyroid conditions, and a whole host of other conditions. So just to reiterate, the three kind of steps we're going to talk about medical technology in are in prevention of disease. So before disease even occurs, trying to prevent it from occurring. In diagnosis of disease, so when disease has occurred, figuring out what's wrong and how are we going to treat it. And finally, the treatment of that disease. So all along this spectrum, and even the places we didn't talk about, medical technology can be really useful. So the first type of technology we're going to talk about is a diagnostic tool called ultrasound. And in order to talk about this type of technology, we have to rewind a little bit. So in our lecture about sound, which I believe is week 10, we talked about sound being waves. And so because it is a wave, it has these waveforms, and we talked about a couple of different characteristics of sound that you can determine from this waveform. So we talked about the amplitude, that is how tall the waves go. And so from the x-axis here all the way to the crest of the wave, you have this amplitude. And so the more intense the sound is, the larger volume it has, the louder it is, the higher this peak is. And if you had a quiet sound, you'd have a pretty low crest and fall. Frequency is inverse to wavelength. So this is our wavelength, our distance between crests. And so if we have a short wavelength, then we have a high frequency, and if we have a long wavelength, we have a low frequency. This translates in sound to pitch. So a high frequency is a high pitch. So if I start talking up here like this, that's a higher pitch than if I start talking down here like this, which is a lower pitch. Sound, since it is a wave, is also directional. And so we also talked about speeds of sound, and the fact that sound moves at different speeds through different mediums. So it moves more quickly through solids and less quickly through liquids, and even less quickly through gas. We talked a little bit about common frequencies, and so we primarily, in our sound lecture, talked about things that are in this frequency here, which is the sonic range. So sonic meaning sounds that we can hear. We also have infrasonic. You might remember infra from infrared. So it's below red. This is below sonic. The frequencies are below sonic. And so this is something like a volcano exploding, where we can't hear it because the frequencies are too low and the wavelengths are too long. And then you can hear everything here in the green. So like lightning or like a chainsaw. And then you begin to get into ultrasonic, so things that are too high frequency for you to hear. So things like bats and dolphins, and also ultrasound. And so the same as with light, ultra means above, so it's above sound in terms of its frequency. We also have hypersonic, so things like jets and planes that are breaking the sound barrier. So ultrasound uses this aspect of sound, that there can be high-pitched sounds that we can't hear, that can be focused in this medical technology. So the ultrasound uses a transducer, which is a part of the ultrasound equipment that includes piezoelectric crystals. And so these are quartz crystals that are aligned in a particular direction. And what's really cool about these is they translate between electricity and sound. So you have electricity that goes into the crystals from your power source, and that electricity gets transmitted into really high frequency sound, an ultrasound. This ultrasound then travels through the body to the particular organ of interest, and then it bounces off in particular ways we're going to talk about, and then comes back to the piezoelectric crystal in this form of ultrasound that echoes. It comes back the same way that we would talk about a reflection in light, and that is then converted by the piezoelectric crystals back from sound to electricity, and that electricity can be used to make an image. So the electric crystals go both from electricity to sound and sound to electricity. And so this is really the core of how an ultrasound works, like how it does what it does. So what does this actually mean? So the color of the ultrasound reflects the strength and position of the reflecting echoes. So as we talked about, the sound moves more slowly through liquids than it does through solids. And in ultrasound, that means that you can't see liquid. And so, for instance, here we have probably the most commonly used form of ultrasound, which is to look at fetuses in utero. So look at a baby in its mother's stomach. And so the reason that this works is because the fetus is surrounded by the amniotic sac, which is full of amniotic fluid. And so since ultrasounds do not show liquid, then you can get through to the solid. So if something, the more solid something is, the more that it's going to reflect back as this white. So you see the outline of the baby here, and it relates to the position that it is. So we can get these really clear images. And the other great thing about ultrasound is they can take place in real time. So very close to real time. So you can have 20 frames per second, and so you get something that looks like a moving picture, a moving baby. And so in this instance, right, where you need a picture of a baby that is moving, this works really well. And other instances where you would want to see possible movement. So again, ultrasound works really well in fluid-filled organs, and in places that you need something to take place in real time. And it's dependent upon the density or how tightly packed the material is that it's going through. So you get these white images when you have denser material. So applications of ultrasound, as we talked about, we have the ultrasound for fetuses, but also you have times where you have something that is solid in places that should have liquid. And so kidneys are not very dense, but kidney stones are solid. So you have a solid in a place that you should have a liquid, or a solid in a place that you shouldn't have very dense material. And so you can see a kidney stone, for instance, right here. And we can also see plaque in veins. So you should have a liquid flow through your vein if you have a solid mass of plaque. Then this is a huge problem, right? It leads to things like heart attacks and strokes. So it would be necessary that we know this and we can look for plaque in veins using ultrasounds. And so we can know where this plaque might be building up. So ultrasounds work really well when we're looking for something solid in something that is filled with liquid. In the next part of our lecture, we're going to talk about x-rays and also a form of medical technology that is used in treatment called insulin pumps.